This is Inorganic Chemistry, Chapter 2, Molecular Structure and Bonding. Section 2.1, the Octet Rule. Each atom shares electrons with neighboring atoms to achieve a total of 8 valence electrons. This is the Octet Rule. For example, in this Bf4- structure, every single atom is surrounded by 8 valence electrons. Boron is surrounded by 8 bonding electrons. Each fluorine is surrounded by 2 bonding electrons and 6 lone pair electrons. There are exceptions. Hydrogen is often surrounded by only 2 valence electrons. Boron, it can be 6, it can be 8. In this case, it's surrounded by 8 valence electrons, but in Bf3, it's surrounded by only 6 valence electrons. There are also third and fourth row elements that can be surrounded by between 8 and 18 electrons. This is because the empty d orbitals, for example 3d or 4d orbitals, can accommodate between 0 and 10 electrons. That's the reason. To draw the Lewis structure in a systematic way, one needs to first count the total number of valence electrons and then connect all atoms with a single bond. How do you make the connection? You need to have some chemistry knowledge about the molecular structure. For example, over here, you don't connect this fluorine with that fluorine. And then we assign electrons to the most electronegative atoms. And then in the decreasing order of electronegativity. So in this case, we assign electrons to fluorine first, and then boron. After that, sometimes you find some atoms have less than 8 valence electrons. And then it's necessary to convert some lone pair electrons to bonding electrons. This is where you make double or triple bonds to make an octet structure for every single atom. And finally, check for resonance structures. Very often, you'll see there are more than one resonance structure. Let's use this as an example. In total, we have 32 valence electrons. 3 from boron, 7 from each fluorine, 1 from this negative charge. 3 plus 28 plus 1, that's 32. First, let's connect all atoms. We make a bond between boron and every single fluorine. We used 8 valence electrons. We have a total of 32 here, minus 8, we have 24. So now we have to give this 24 electrons to the most electronegative atoms first, so fluorine. We give this fluorine 6, now it's an octet, another 6, 6, 6. We used up all 24 electrons. Now let's look at other atoms. This boron, well, it's surrounded by 8 valence electrons. It's good. We stop here. We skip step 4. Now step 5. Check for resonance structures. So there's no resonance structure. But wait. Well, if you have to, you can actually give this 2 bonding electrons back to this fluorine atom. So then you have Bf3, neutral, plus F minus. Well, is this a legitimate Lewis structure? Well, more or less. Although this boron in Bf3 is surrounded by 6 valence electrons, but it's common for boron compound. And then you have a separate F minus. Actually, this F minus is surrounded by 8 valence electrons as well. So actually, in this sense, it's possible to draw 4 more resonance structures by giving this 2 electrons to this fluorine, or this 2 electrons to this fluorine, this 2 electrons to this fluorine as well. Now let's look at another example. Let's look at carbon monoxide. First, let's count the total number of valence electrons. It's 10. And then we connect all atoms. Well, there are only 2 atoms, so we put a single bond in between. So 10 minus this 2 bonding electrons, we have 8 more to give. We give oxygen first. And oxygen is now surrounded by only 2, so we give oxygen 6 more. Oxygen gets 3 more lone pairs. There's only 1 pair left for carbon. So we got this structure. 3 lone pairs for oxygen, a single bond in between. Carbon gets only 1 lone pair. Look at this one. Oxygen is good, but carbon is not. Carbon is surrounded by only 4 valence electrons. Now, step 4. Let's make double or triple bond. So first, let's move this 2 electrons to here in between. So oxygen does not really lose these 2 electrons. By putting these 2 electrons in between, this oxygen is still surrounded by these 2 electrons. At the same time, carbon is now surrounded by 2 more electrons. So carbon is surrounded by 1, 2, 3, 4, 5, 6. Carbon is surrounded by 6 valence electrons. Better. Now we can again, give 2 more electrons to here, and then both carbon and oxygen have reached the octet structure. Finally, let's look for resonance structure. There's no other resonance structure for this molecule. One more example. SO3. First, count the number of valence electrons. There are 24, 6 from each atom. Sulfur sits just below oxygen. They're in the same column in the periodic table. And then we connect sulfur with the 3 oxygen atoms, each with a single bond. That means we'll have to use 6 valence electrons. There are 18 left. And then we assign electrons to the atoms with the highest electron negativity first. That's oxygen. So each oxygen gets 3 lone pairs. Now we have no more electrons left. Alright, it's going to be just sulfur forming 3 single bonds with 3 oxygen atoms. Each oxygen atom is in addition surrounded by 6 lone pair electrons. So for oxygen atoms, well, they achieved the octet structure. That's good, but sulfur is surrounded by only 6 valence electrons, the 3 single bonds. So why don't we just make a double bond then? We actually ask one of the oxygen atoms to share 2 lone pair electrons. So in this case, this oxygen give 2 lone pair electrons to form this SO pi bond. Now you have a double bond here, sigma bond, pi bond. Okay, so now you have this oxygen still surrounded by 8 valence electrons. Now this sulfur is surrounded by 8 bonding electrons, so it's good. Now let's look at the formal charge. If we look at the oxygen, it's surrounded by 1, 2, 3, 4 lone pair electrons. It's not drawn here. You imagine there are 4 lone pair electrons here, 2 lone pairs, and then 4 bonding electrons. Alright? But when you look at a bond, to calculate the formal charge, you just assign half of the bonding electrons to oxygen, the other half to sulfur. So we just assign 2 to oxygen plus the 4 lone pair electrons. We have a total of 6 being assigned to oxygen for the purpose of calculating the formal charge. 6. How many valence electrons does a free oxygen atom have? 6. So the formal charge is 0. Now let's look at sulfur. So we give only 2 electrons to sulfur, 1 electron to sulfur here, 1 electron to sulfur here. So sulfur is surrounded by a total of 8 bonding electrons. Only 4 are assigned to sulfur for the purpose of calculating the formal charge. And then, if you think about it, sulfur, a free sulfur atom, should have 6 electrons. Now it has only 4. So it's plus 2 plus charged. The formal charge on sulfur is plus 2. Now this oxygen is surrounded by 6 lone pair electrons, and then there's a single bond here. So a total of 8 electrons. The 6 lone pair electrons should be assigned to this oxygen for sure. And then to calculate the formal charge, we take half of the bonding electrons. So 1/2 times 2, that's just 1. We give this 1 electron to oxygen for calculating its formal charge. So oxygen is surrounded by 7 electrons for the purpose of calculating the formal charge. And supposedly it should be surrounded by only 6, now 7, so it's negatively charged. Minus 2 plus 0. Now let's check for resonance structures. You don't have to form the double bond here, you can form it here or here. So we have 3 resonance structures. In each of the 3 resonance structures, the sulfur has a 2 plus formal charge, and 2 out of the 3 oxygen atoms has a -1 formal charge. This 2 or this 2. Well, actually, these 3 resonance structures are not the most favored Lewis structure, they actually have higher energy than this one. In this one, sulfur forms a double bond with each of the 3 oxygen atoms. The reason this one is preferred with lower energy is because we need to minimize the number of formal charges. Alright, so you have 2 charge here, you have 1 charge here, you have 1 charge here. Don't worry about sign. Alright, you have a total of 4 formal charges. 1, 2, 3, 4. 1, 2, 3, 4. Over here, 0. But wait, sulfur is surrounded by 12 body electrons. Is that possible? Yeah, it is. Sulfur is a 3rd row element. The 3D orbitals of sulfur can be used to accommodate additional electrons. So in this case, it's possible for sulfur to have this 1, 2, 3, 4, 12 valence electrons. And again, let's look at the formal charge. The 12 bonding electrons, we assign half of them to sulfur, that's 6, and that gives you a formal charge of 0. And for oxygen atoms, and you can see we assign this only 2 bonding electrons to this oxygen. So 6 in total assigned to this oxygen on top. Therefore, the formal charge of the oxygen is 0. Now let's look at the Lewis structures of some simple molecules. Each hydrogen is surrounded by 2 valence electrons. Each nitrogen is surrounded by 8. Carbon and oxygen, both octets. This is ozone. If you look at this structure, 1, 2, and then 8. 1, 2, 3, 4, 5, 6. 6 bonding electrons plus 2, 8. And over here, 8. But look at the formal charge. Look at this one. If you look at this one, this oxygen is surrounded by 1, 2. Since we're talking about formal charge, we give this electron to this oxygen. We give 2 of the 4 bonding electrons to this oxygen. So it's surrounded by 5. Supposedly, it should have 6. So this oxygen in the middle is plus 1 charged. This is plus 1 charged. And this one is minus 1 charged. Why? We give 1 of the 2 bonding electrons to this oxygen. So 1 and then plus 6, that's 7. 1 more than necessary. This one has a negative formal charge. -1 plus 1, 0. -1 plus 1, 0. So this is not really stable. You need to give this 2 electrons to here. And then you have 0 formal charge, 0 formal charge, 0 formal charge. When the sulfur forms 2 double bonds with these 2 oxygen atoms. In that case, the sulfur will be surrounded by 10 valence electrons. That's okay. That's okay. Because sulfur is a 3rd row element. It can accommodate more than 8 valence electrons. Can you do the same thing? Can you share this 2 electrons? Can you put this 2 electrons over here to form a double bond? No. This is because oxygen is a 2nd row element. You do not exceed 8 valence electrons for any 2nd row elements. So now for nitrogen, NO2 minus here. So just picture this NO2 as just ozone. So N minus has 6 valence electrons just like oxygen, right? N minus. N nitrogen has 5 valence electrons. So N minus has 6 valence electrons. So this N is the same as O as the number of valence electrons. So basically just copy this structure, put it here. Indicate the negative sign, change oxygen to nitrogen, and that's it. Both ozone and this NO2 minus have a resonance structure. Basically, just swap the situation between these 2 oxygen atoms. So you can put the double bond here, and then you can put 1 additional lone pair here. Same here, put the double bond here, and give this additional lone pair to the oxygen on the right. Ammonia is surrounded by 8 valence electrons here, and this is SO3. But again, this structure is not the most favored structure. This sulfur has a 2+ formal charge, -1, so it's not the best structure you can draw. You can simply draw actually 3 double bonds, and then you make the formal charge of every atom 0. That's good. This is PO4. In PO4, there's 3 minus charges. So this is good. Minus 1, minus 1, minus 1. In this case, do not make 4 double bonds. If you do, well, you will see the total formal charge is still 3. Okay, the absolute values, it's still 3, and yet unnecessarily you have a total of 16 electrons surrounding this phosphorus. That's just too much. I mean, it's possible for this phosphorus to accommodate up to 18 electrons, but if you put 18 electrons surrounding this phosphorus, the electron repulsion can be pretty big. So this is actually the favored Lewis structure. Again, 3 single bonds here, 1 double bond. And you have a -1 formal charge on oxygen, -1 here, -1 here. 0 formal charge on this phosphorus, 0 formal charge on this oxygen. So that's good. That's good. There are 3 other resonance structures, of course. You can form the double bond here, here, or here. Now, similarly, S2 minus is equivalent to P3 minus. So, not much to say here, but in this case, what you want to do is you have this -1 charge here. You have -1 charge here, and you have formal charge of 0 here, here, and here. Look, this sulfur is surrounded by how many valence electrons? 4, 4, 2, 2, a total of 12. A total of 12. So sulfur is surrounded by a total of 12 valence electrons. So that's okay. And half of this 12 should be assigned to sulfur when calculating its formal charge. Half of 12, that's 6. So 6 is fine. 6 is fine. All right. This is ClO4 minus. ClO4 minus. So now this chlorine is surrounded by a total of 14 electrons. So a total of 14 electrons. And if we look at the formal charge, -1 formal charge here, 0, 0, 0, 0. So that's good. We minimized the number of formal charges. Well, if you wonder, maybe I can just move this 2 electrons to here. This 2 electrons to here. It's possible. And then you will have -1, -1, plus 1. -1, -1, plus 1. If you sum up their absolute values, you get a total of a total formal charge of 3. So -1, -1. You count, you sum up their absolute values, you get 3. So it's bad. So this is more favored with lower energy structure.